All right, so welcome back everyone to the RL theory seminars. Just to kind of like reiterate how these seminars work. So the presenter has 50 minutes to present, that's 50 minutes. And throughout the presentation, you can just feel free to unmute and ask any questions. If you want to ask your questions in the chat, feel free to do that as well. I'll read out your questions to the presenter. Yeah, and so during the presentation, we have a co-host. So Kiara is going to be the co-host, and she'll just be stimulating the presenter with more technical questions if there aren't others. I'm also going to share the slides in the chat right now. So if you want to follow along that way as well, that works. Otherwise, I'm going to go ahead and introduce the presenter for today. So today's presenter is Hui Zhu. And she's currently a graduate student researcher in the computer science department at UCLA. And before joining UCLA, she received a bachelor's and a PhD degree in mathematics at the Peking University. Her research centers on the theoretical and practical aspects of optimization, machine learning, and reinforcement learning, with applications in the fields of medical imaging and drug discovery. Otherwise, feel free to start the presentation.
Okay, thank you for the introduction, and thanks for the organizers for this great seminar. And it is my greatest pleasure to be invited to present our work on a general framework for sample-efficient function approximation in RL. And this is joint work with Zixiang Chen, Chris Jinchi Li, Quanquan Gu, and Michael Jordan. And some of my co-authors are also in the audience, and welcome. So let's start with some preliminary background. And we are interested in the reinforcement learning algorithms for decision making, and which has witnessed remarkable empirical success in a wide range of domains. And some of the most popular applications include like DeepMind's AlphaGo and AlphaZero, which conquered the complex games of Go and chess. We've also seen Meta's Rebel playing the game of poker, and OpenAI's robot arm solving the Rubik's Cube, and autonomous driving, and so on. And given the difficulty of simulating data, it is crucial to reduce the amount of data required for RL tasks. However, due to the intractably large state and action spaces that are used to model the real-world complex environment, training on the original state and action spaces can be cumbersome. For example, for the simple tabular MDP case, the sample complexity is dependent on the cardinality of the state and action spaces. Therefore, function approximation in RL has become prominent in both algorithm design and theoretical analysis. So in the rest of the presentation, I'm going to introduce a unified algorithm that addresses almost all known solvable MDP cases and illustrates how it achieves or supersedes the state-of-the-art sample complexity when restricted to the specific instances. And since everyone here might be familiar with the definition of MDP, I'm going to briefly go through the basic settings and notations just to clarify the assumptions and objectives of our work. First of all, a Markov decision process is a tuple with S as the state of feasible states and A as the action space. H is the horizon for each episode. P is the transition probability, and R is the reward function. And in an RL environment, the agent interacts with the environment via actions determined by a policy pi, and the corresponding Q and value functions can be defined as the expected future reward. The Q function and V value functions can be related to each other through the Bellman operator. Specifically, we define the Bellman operator as the expected value function at the next step with the expectation taken on the transition kernel plus the reward function. And the optimal policy is defined as the one that maximizes the expected total return, and we denote it as pi star. Accordingly, induced by the optimal policy, we have the optimal Q and V value functions as V star and Q star. And the objective of RL is to know a policy that is within an epsilon range of the optimal policy. And to estimate the sample efficiency, we compare the sequence of policies generated by the agent pi-t to the optimal policy pi-star. We define the cumulative regret as the sum of differences in value functions induced by pi-t and pi-star along the trajectory. So there is a rich literature on RL models. Among them, there are tabular MDP, factored MDP, linear and linear mixture MDP, kernelized nonlinear regulators, and so on. And all of the assumptions here can be divided into two categories. Basically, they are model-based and model-free settings. For the model-free setting, the assumptions is added to the value function. And for the model-based settings between the agent and the environment, we first estimate the true model before interacting with the agent. So there are several works studying a general function approximation.
Sorry, can I just clarify something? When you're talking about model-free and model-based here, are you talking about the algorithms or is it a design
It is
feature?
the design. It is the,
okay. So could you go over again how it fits into the design?
So for the model-free case, it is designed like adding assumptions on the value function. But for the model-based case, the assumptions are added on the estimated model.
I see. Okay, thank you.
So for the general function approximation, there are also several works, including the Bellman rank and the Inoue dimension and the Bellman Inoue dimension. These three are model-free assumptions. They are based on analyzing the expected Bellman residue. And on the other hand, the witness rank by Sun et al., it is a model-based assumption, and the bilinear classes by Zhu et al., it encompasses both the model-free assumptions and the model-based assumptions. Also, there's a framework called DEC by Foster et al. It provides a necessary condition for efficiently solving the decision-making problems. In our work, we focus on both the generality of the assumptions and the sharpness of the sample complexity. We provide a unified framework that includes all model-free and model-based RL classes while maintaining sharp sample complexity. Therefore, like for nearly all models that we see in practice or potentially new models to be seen, we have a single unified algorithm that works for all. In this picture, we visualize and compare prevailing sample-efficient RL frameworks and ours in this figure. And as by far, the richest concept is the DEC framework. It's a necessary condition for sample-efficient interactive learning. And Bellman-Inoue dimension is a rich class that assumes both Bellman rank and low Inoue dimension. And it addresses almost all model-free RL, and generalized bilinear classes captures model-based RL, including KNRs, linear mixtures, and low witness rank, but it does not include the Inoue dimension-based models. And our ABC class encloses both of these previous classes, except for the DEC. And in the following table, we compare our ABC framework with other structural RL frameworks in terms of the model coverage and sample complexity. Basically, we compare with bilinear class no and low Bellman-Inoue dimension and the Bellman representability proposed in the DEC framework. And for model-free models, including the linear MDPs, the low occupancy complexity, and linear Q star V star model, all complexity is the same with the low B dimension case, and is better than the other two. For the linear mixture model, the BE dimension does not address the model-based case, and the sample complexity is also the best. And for the Bellman rank, it's also a model-free model, so it's the same with the other models.
Sorry, I just have a quick question. Like, is this the results? Are these like upper bounds for an algorithm?
Yeah, it's an upper bound on the sample complexity.
And this is like what algorithms are being used here? Because I just see like these are like complexity measures in the headings.
We use the algorithm proposed in each framework, like for in their original paper.
Okay, so like in DEC, there's like E2D being used here.
Yeah.
And in yours, there's some algorithm that you'll talk about later.
Yeah, exactly.
And what does this low FE mean?
Low FE dimension is a concept that we will introduce later. It's similar to the BE dimension. It's more powerful. Yeah.
Okay, got it. And these are all upper bounds, right, for the algorithms?
Sorry?
These are all upper bounds.
Yeah, these are all upper bounds.
Okay.
So for the eluder dimension, that it's also model free, but bilinear class does not cover this case. And for the witness Yuan can kernelize nonlinear regulator, which is the KNR, we provide sample complexity, and we will show later that it is comparable with the sharpest result under the specific models designed for the specific instances. And all the other frameworks for the BE dimension, it does not cover. For bilinear class and DEC, it covers, but they do not provide explicit sample complexity analysis under these frameworks. And also their complexity, it would be worse than ours if there is an upper bound. And next, we introduce how we define a general framework, and we call it the admissible Bellman characterization, the ABC class. First, we assume that there's an MDPM, and our goal is to search our best model or say hypothesis within the hypothesis class, identified by the QV pair. The same notion has been used in Zhu et al. For example, for model-free assumptions, we can define the hypothesis class via the union of Q, and V follows the max Q principle. And for model-based assumptions, the hypothesis class can be identified by the optimal value function under the given transition probability. And we use O as the per step observed transition tuple. And there's also a discriminator function class V, which is similar as in the IPM, which is the matrix of similarity between probability. And it is designed to accommodate the witness rank case. And we also have a function, we call it the coupling function. It is used to measure the interaction between F and G. And the estimation function is a surrogate loss function of the Bellman error, and we will introduce it in more detail later. Also, we have two assumptions. The first one is the realizability assumption, which assumes the true model belongs to the class. And the second is the generalized completeness. And we have an auxiliary class G that includes all functions after Bellman operator operated on F. And then the ABC class is defined when we have the dominating average estimation function, and another condition is the Bellman dominance. For example, when taking the estimation function as the Bellman residue, and we see that one possible choice of our coupling function here is just taking it to be as the expectation of the Bellman residue. And under that circumstances, it reduces to the low BE dimension. And we will mention later that the estimation function does not have to be Bellman residue, and the coupling function does not have to be it does not have to be linear. But if the coupling function is in the form of a bilinear term, it reduces to the low Bellman rank.
So there's a parameter kappa there? What's the kappa?
The kappa is the constant between 0 and 1.
Okay.
So it's just to make the framework more general, like in the KNR case, we might need to use the kappa.
Okay, so you're basically assuming there's your G is such that it dominates it's less than the average estimation function, but it's bigger than the Bellman error.
Yeah, exactly. And when the estimation function is exactly the Bellman error, we can take the coupling function to be the expectation of it.
Okay, yeah, that makes sense. Thank you.
So for the functional in-order dimension, we define it as the length n of the longest sequence, such as for any sequence with length less than n, and when we limit the sum of squared g function on the sequence to be less than epsilon square, and we can still have an element that has absolute function value that is larger than epsilon. And for example, like in the previous example, if we define the coupling function to be the expectation of the Bellman residue, and the functional in-order dimension reduces to the Bellman in-order dimension. And if the also in the previous example, if the coupling function is a bilinear form with dimension d, the functional in-order dimension is also in an order of d. So this FE dimension is a more general notion of complexity measure, and we'll see later in some specific examples that this generalization sometimes improves the sample complexity. And next, we introduce the decomposable estimation function. This is these are two assumptions added on our estimation function. The first one is the decomposability. This is inherited from the Bellman error. And the next is global discriminator optimalities. This is designed actually for the witness rank also. So there's a discriminator class V, and we assume that there exists a global maximum V star, such that the norm of expected estimation function on V star is larger than the norm of expected estimation function on all other V. So when the estimation function is exactly the Bellman residue, we see that the decomposability, if you take expectation and estimation function minus the expectation on the next step, it equals to the estimation function on the Bellman operator operated on the function itself. So basically, the decomposability holds for every every model assumptions that we will talk about later. And actually, we can almost always design an estimation function that satisfies the decomposability if we define it as an expectation of something minus the function itself. So, and the global discriminator optimality requires rich enough discriminator function class, and it is generally satisfied by existing MDP models.
Can I ask a question about this discriminator? So in the loss function example you've given there, I can't see how little v comes into it.
The discriminator function class we'll talk about later, actually. Like, yeah, it will. Yeah, it shows here for the dominating average estimation function, we take the max over the discriminator function. For example, if you want to estimate like the Bellman, like the witness rank, you use the discriminator function to measure the discrepancy in distribution of the true model transition kernel, and you assume the model transition kernel. So you use the estimation function to estimate the distributions in transition kernels, and you take max of it. And our dominating average estimation function is defined via the maximum over all discriminator function class.
So you sort of pick the discriminator based on which sort of dimensionality metric you want to appear, dimensionality measure you want to appear in your graph. Is that what you're doing here?
What do you mean?
So you're picking your discriminator function class based on the knowledge of what you're aiming for in your regret bound. So if you're aiming for witness rank, I think you said, then
Yeah.
you're picking.
Yeah, normally our discriminator function class would be like, for example, take all functions that with L1 norm less than 1.
Mm-hmm.
Such kind
Yeah,
of
I
classes.
think Quan has just said in the chat, it's a function being maximized in a dual form of integral probabilistic. Sorry, the dual of what?
Oh, yeah, I was trying to say that, for example, because in some model-based IO, we need to measure the distance between the true model and the estimated model. And in this case, we can use total variation distance or what's a stand distance. And all of these distances can be defined as maximizing some function within certain function class. This is called the dual form of, for example, what's a stand distance. And the function being maximized there actually is the function we call it a discriminator function in the definition shown on this slide.
Okay, so if I define the distance between my transition functions in terms of the total variation distance,
yeah,
the discriminator becomes a dual of that?
No. For example, you are using the total variation distance, and total variation distance can be defined as maximize the some function.
I see. Yes. Yes. Okay. Yeah. And then it's the one that. Yeah.
Exactly.
Thanks very much.
No problem.
So one final question. Does this only come up for model-based then? Or does the notion of this discriminator function appear in model-free frameworks as well?
The discriminator function, it appears in the witness rank definition, so it is a model-based model. We've not seen a discriminator function in model-free case before, because it is used to measure the discrepancy between the transition probability. So normally in the model-free case, we don't need the discriminator function class.
Yeah, that makes sense. Okay, brilliant. Thank you. I'll let you carry on. Sorry.
Okay, thank you. So yeah, for the decomposability and global. Yeah. So next, we introduce some specific MDP instances that satisfies our assumptions, and we illustrate how our framework works. The simplest example is the linear mixture MDP. The linear mixture MDP is defined such that the transition kernel and the reward function is linear in two feature mappings. And the transition of the next step and the reward function will be uniquely given by a parameter theta. So theta star is the optimal model or the true model, and theta h is our assumption. So under this case, the hypothesis class is defined as the union of all parameters theta h. And we design our as decomposable estimation function, or DEF, with two hypotheses G and F prime, and it is defined as the difference of two terms. On the left-hand side, it is the transition kernel plus the reward kernel times the parameter coming from the model G. We see that although the parameter comes from the model G, the kernel comes from the estimation of value function of model F prime. And on the right-hand side it is the reward and the value function of F prime. So it is the expectation of the right-hand side minus the right-hand side. And if you take expectation of the DEF here, we see that it equals to the difference between the model G and the true model times the transition kernel and the reward kernel. So the above expectation of DEF measures the discrepancy in optimality between G and F star. And on the other hand, the expectation of Bellman residue is in a similar form. It's actually in the same form. It's the discrepancy, the difference between theta F and theta star times the expectation of the kernels. So based on our definition of the Bellman dominance and the dominating estimation function, it belongs to the linear mixture MDP belongs to our ABC class with the coupling function defined as the product of the difference in parameters times the expectation of the kernel. And if the dimension of the parameters is D, we've seen that the FE dimension of the coupling function on the hypothesis class of linear mixture MDP is also D. And another example is the low witness rank model. So it is a model-based assumptions that covers several specific instances, including the factored MDP, and also it covers the low witness rank case. And as we've introduced before, there's a discriminator function, and there's a hypothesis class and two mappings X and W. So the witness rank is defined by two conditions, and there's like the maximum of the discriminator function of the expected difference in the transition probability. Like the transition like we use the discriminator function V to measure the difference between GH and PH, and we take expectation and takes the maximum over V, and this should be larger than a bilinear product. And also on the other hand, the expectation of the Bellman residue is less than the bilinear product. So under this case, the hypothesis class is defined as the model class, the same as the witness rank. And we choose the DEF also with two models, G and F prime. And the DEF is defined as the expectation with respect to G on V minus V itself. It is actually independent of F prime here. So for this example, the expectation is just equals to the difference in transition probability when measured with discriminator function V. So also the above, also we see that the expectation of DEF measures the discrepancy in optimality between G and the true model. And on the other hand, the expectation of Bellman residue is by definition less than the bilinear form. So in this case, we can define the coupling function as the bilinear product, and the FE dimension is also D. The last example we are going to talk about is the KNR case. So it's a nonlinear control dynamics on an RKHS of finite or infinite dimension. So there's also a feature mapping, and we assume that the next state is a Gaussian distribution centered on the product of the feature mapping and the parameter U. And the hypothesis class is defined by the union of all possible UH. And the DEF here is the expectation of the next step H, which is U times the feature mapping minus SH, S at the next step. So for this example, the expectation, we can see that it is also a discrepancy in optimality between G and the true model. And on the other hand, for the KNR case, we can prove that the expectation of Bellman residue is is less than a parameter times the expectation of the norm of the discrepancy of in parameters times the feature mapping. So we see that here there's there's a constant parameter here. So this is where kappa goes in our definition. So it belongs to our ABC class if we define the coupling function as the square root of the expected squared norm of the function we care about. And we can prove that even with the squared norm, like even if we see that the coupling function now is not a bilinear form, so even with the squared norm, we can still prove that the FE dimension of the hypothesis class with respect to the coupling function defined here is the dimensionality of the mapping phi. So we summarize the properties of our ABC class. We recall that there's dominating estimation function and Bellman dominance. And first of all, we've seen in the previous KNR example that the coupling function can be nonlinear. So there's also another example about the generalized linear Bellman complete. It is a squared root of a bilinear form. So this achieves optimal sample complexity. Like if you always assume that the coupling function should be a bilinear form. So in some cases, the Bellman dominance condition would be the squared norm of a bilinear term, and it brings extra computation in the sample complexity. And in previous works, when they do not design the estimation function as in our coupling function, when they do not design the coupling function as in our way, their sample complexity cannot even achieve square root of their regret bound cannot achieve the square root of t. Also, the estimation function can be different from the expected Bellman error, and this is designed for any model-based cases. And there's the dominating average estimation function L can be larger. For example, in the linear mixture MDP, it's greater or equal than instead of equal. So the Bellman dominance condition can also be smaller, like in the KNR case. And our estimation function can be vector valued. And next, we introduce our algorithm and main results here. Given our definition of our estimation function, we design our algorithm as in an optimism principle, like in the upper confidence bound algorithm. We always take the argmax of our value function within the hypothesis class subject to a confidence region, and the confidence region is defined by beta, and it is centered around the infimum of the sum of the squared norm of estimation function. And in some cases, the infimum can be explicitly solved. For example, if it's linear in the linear mixture MDP or KNR case, the right-hand side can be explicitly solved. So based on that principle, we can prove for sample complexity result. And we recall that the regret is defined as the summation of difference in value functions between the optimal pi star and pi t. And since in each step, we always take the argmax of value function in a confidence interval, and if our choice of beta satisfies that our optimal model is within the confidence interval, the regret we want to estimate can be upper bounded by VFT minus V pi t, which is the model we assume at ft minus the model the value function when we operate the actions by pi t. So by the decomposability lemma, it can be decomposed into the summation on the trajectory on the expected Bellman arrow. Therefore, based on our Bellman dominance condition, the regret bound can be summarized as estimating a summation of our coupling of the absolute value of our coupling function. So on the other side, based on the martingale concentration argument, which is specifically we use the Fresman's inequality, we can bound the summation of the coupling square norm of coupling function within a confidence interval of beta. So overall, based on the properties of our Fe dimension, we can control the summation of the absolute value of the coupling function by the square root of the dimensionality times beta times t. And here comes our main theorem that for an MDPM and with the hypothesis class we introduced before and under our ABC structural assumptions, we have with probability at least 1 minus delta, the regret can be bounded by h times square root of t times the dimension and the Fe dimension times beta. And this upper bound is dependent on both the functional Euler dimension Fe and the covering number n on the function class. So for cases with a linear structure, for example, linear or linear mixture MDP or the Bellman rank or the low Bellman rank or any other linear structures with dimension d, the regret bound reduces to dh square root of t, where the t is the number of episodes.
Can I just clarify what calligraphic L is here? The function class you're covering, is this the class of your loss functions, or?
F is the class of the hypothesis classes, like the model assumptions.
And L?
L is the estimation function. L is a larger. It's a larger set. It includes the hypothesis class F and G, and also includes the estimation function class. So we have to assume that we have to make a cover on everything.
Okay, so it includes the hypothesis class under the Bellman operator, and your class of losses, which or I think you're calling them estimation functions. That's your little L, right? Yeah.
But basically, if your model is linear, so everything is in dimension d, and the covering number is also like the log of the covering number is also d.
Okay, thank you.
So next we see some implications on specific MDPs. First of all, we come back to the linear mixture MDPs. We recall that our algorithm design is based on the optimism within a confidence region. And for the linear mixture MDPs, when the right-hand side of the infimum can be explicitly solved, it is the theta hat is the solution to the value targeted regression, as in the UCLA VTR algorithm. So here in this example, our confidence region reduces to a confidence region centered around theta hat and with diameter beta. And so the difference of the linear mixture MDP's algorithm in our framework with the UCLA VTR proposed in Jin et al. On linear mixture MDPs is that we are operating a global optimization, and UCLA VTR is optimization step by step. And on the linear mixture MDP case, it exhibits a dh square root of t regret bound and d square h square over epsilon square sample complexity result. And compared with previous frameworks, like we've already seen in the table, and the previous sample complexity is d to the power of 3, h to the power of 4 over epsilon square. which is the best known result on general frameworks that subsumes linear mixed MDPs. And another example is the KNR case. For that case, if we bring the estimation function into the definition of the algorithm, we can also explicitly solve the right-hand side infimum, and the confidence set is also a confidence region defined around the solution, which is U hat. And it is the optimal solution to a least square problem. So it also reduces to another algorithm on KNR, which is LC3 by Kakade. It is an inhomogeneous version of that algorithm, and it achieves a regret bound that matches the state-of-the-art regret bound. And the last example is the low witness rank case, which is slightly more complicated because we need to take the maximum over all the discriminator functions. And here, by definition, the estimation function is the expectation of on the function on the hypothesis class F minus V. So the confidence region is defined as the summation of the square norm of the estimation function minus the infimum of the same term, and it's within a range with diameter beta. So it outputs an epsilon optimal policy within h squared times the number of the cardinality of the action space times the dimensionality of the witness rank model times beta, and divided by k squared epsilon squared. So previous best known sample complexity result, even when specified to the witness rank model, it is h to the power of 3 and the dimension to the power of 2. So our sample complexity is superior by a factor of dh up to a polylogarithmic prefactor in model parameters. So overall, there are some takeaways and conclusions of our work. So we design a unified framework that subsumes nearly all solvable MDP models, including model-based and model-free models. And we design a new type of estimation function for optimization-based exploration that can be vectors. So, and the proposed functional eluder dimension with a sample efficient, and also we design a sample efficient algorithm. We call it the Opera algorithm. And thank you for listening. And this is our paper. And so, welcome to check our paper for more details. Do you have any questions?
I have lots of questions. So, I mean, I'm happy for other people to start with their questions, or I could just jump straight in.
I have a quick question, kind of earlier on. When you're like in that table, or well, actually, is there any lower bounds? I mean, more.
Yeah, we analyze all upper bounds where the lower bounds in the specific examples that we can compare our upper bounds with the lower bounds. For example, in the linear MDP, the lower bound is d square h over epsilon square, and there are some cases, but we do not. We leave the lower bounds of our general framework as the future direction.
Mm-hmm.
So, like we compare our upper bounds with lower bounds in the specific instances.
Mm-hmm. Okay, I see. Yeah, because okay. And this DC results they're using here, is this the newer results that they have with their constrained DEC stuff. I don't know if you know what I'm talking about. There's like the tight guarantees paper.
Yeah, the DEC, the constraint DEC is a new work that we haven't compared with our work right now. But their algorithm, basically the DEC algorithms are also are all based on the posterior sampling algorithms, and our algorithm is an optimization-based algorithm. So
I guess I'm just asking how the results compare in the table when you were to compare to the newer one, because right now there seems like there's gaps everywhere. Like yours is just strictly better for almost all of these.
I guess.
And maybe can you explain in the like you had the nice diagram before of all the different other complexity measures. What setting exactly is the DEC catching that yours isn't? Like what actual?
Actually, it is. There are no like we haven't like in all examples that we've seen in our literature, there are no specific examples that we can find that is covered within DEC, but not covered in all framework. It's like all existing assumptions that we can find is covered by our model. But we do have some instances that is not covered by our model, but it's also not covered by DEC. It is called I think it's the Q star state aggregation or something.
Okay, sure. So technically, so you're just conservative in this picture in the sense that the ABC might cover everything that DEC does, in the sense that you haven't found a setting where DEC covers that ABC doesn't?
Yeah, in definition, DEC is the largest and it covers all, but there, I think the specific instances are still to be discovered.
Oh, I see. Okay. Yeah, and there's a person that raised his hand. You can just unmute and ask your question if you want.
Yeah, I think I'll ask and leave because they're about to lock the doors of the office. So yeah, I typed it, but like you already raised it. Any insights or comments on like how this can be extended to include the linear Q star or the state action aggregation, sort of the two things that were left outside by the ABC, or is it? Do you see any way out for this, or is it really not trivial?
That I'm not sure about that, because the two examples excluded by our ABC class, I think it's hard to design a sample efficient algorithm. I remember that it is yeah, I've thought about that, but it's not that trivial. Like all the previous frameworks, is hard to cover these two instances.
Yeah, great, thanks. I'm going to head out now, just hunting for future work. So thanks, it's open then.
Yeah, thank you.
So just following on from that, what exactly makes these linear Q star so different to these? That means it's.
Can you actually explain what you mean by linear Q star? Maybe I'm missing something here too. It's just like the Q star is linear?
You mean the linear Q star?
What's the definition of this?
The definition of linear Q, like the
linear Q star means the optimal Q function can be written as like a feature map, for example, phi A times some theta. Yeah.
Okay, so it's like the Q pi realizability stuff, but just for Q star, right? So there's
and there's a lower bound.
Yeah, I know.
Yeah, there's a lower bound, right? Yeah, I'm getting confused.
So I'm confused. Is the question here?
I'm confused now.
Get an efficient algorithm, or I thought like, don't you still get like your complexity measure would output like some value for this setting or something, right? And then
right. There's an exponential lower bound. Unless it's a deterministic.
Yeah, right.
But I guess your question of whether your complexity measure could get that exponential result, I guess. But then I don't know. Is it trivial to get an exponential?
Yeah, what's the question? I guess I'm confused. Like what? What is the open problem part of the linear Q star?
I think probably you need further assumptions to make it reasonable. But typically the assumptions are like low Bellman error or low Eluded dimension or something. So
I guess the question is, like, when you look at the linear Q star setting and you look at what the value of the complexity measure is, what do you get for the algorithms like upper bound? Is it exponential or something? Like, is there a problem? I don't know if that makes sense. Does the question make sense? Sorry.
Yeah, given the exponential lower bound for linear Q star, and I think because the linear Q star cannot be okay. In order to apply our framework, we need to figure out what's the function class, what's the estimation function, and in this case, we don't need to worry about discriminator function. But even for the estimation function, in order to apply it to Q star, we need to make sure it satisfies those two properties. But I highly doubt we can come up with a coupling function and estimation function such that those two inequalities will hold. So in that case, in that sense, I don't think we can plug in this linear Q star case into our framework. Yeah.
Right, because I guess for D, yeah. Okay.
So maybe sort of related to that, you're saying that you need to know your function classes to be able to define your algorithm. Do you think there's any hope of developing an algorithm that is able to just adapt to know, like, for example, something about it, but not all the details, and then be able to capture all these sort of dimensionality measures at the same time? Do you think that's possible or not?
I think that the difficulty here is not about choosing the function class, because if we know, for example, Q star is linear, we can.
Sorry, I meant more generally, rather than just in the linear Q star setting in a more general sense.
I see. Yeah, I think the implicit assumption we are making here is the function class we are using need to have a bounded functional eluded dimension, because this term will appear in our regret bound. And for most of the MDV instances we've seen here, actually, they are either have their functional eluded dimension actually is bounded. And if it's a linear function class, the functional eluded dimension just equal to the eluded dimension, which is further equal to the D, which is the dimension of the Euclidean space. So, and of course, this result can be applied to kernelized space, where I guess the functional eluded dimension can be bounded by some effective dimension in certain architectures, reproducing kernel Hilbert space.
Yeah. So my headphones died halfway through that, so I missed a little bit of your answer. So maybe you did already cover this, but like, from what I can see, when you want a regret bound that depends on the witness rank or something like that, you'd specifically define your loss function or your estimation function in a particular way.
Yeah.
Do you think there's any hope of being able to define a more general loss function that will allow you to get the witness rank when that is the dominating feature of the problem, but also get some of the other complexity measures when those ones turn out to be what's making the problem difficult? Does that make sense?
I see.
By the loss function, like the estimate.
Your little L, you called it something else.
Actually, like the little L here, if we do not use the, wait, let me first go back to the witness rank. Yeah, let's go to the algorithm. So, like, if we do not use the little L here is just a summarization that it is the expectation of V minus V itself. Like, we don't need the I'm not sure if it's what you mean, but if we don't explicitly write out L here, it is also measurement of difference of the function. We need a hypothesis class F at least. So the expectation with respect to the hypothesis class on V minus V itself, like we don't need anything else to design the algorithm.
But I guess your result depends on the particular choice of V. Maybe it doesn't.
For this example, yes, but for most other examples, we don't need this discriminator function because
but V in general is the, like we previously talked about, is a ball, like the L1 ball or L infinity ball. It's just a very general function class that is within language.
And so, have you come across any settings where this is a bit of a mean question? So sorry about this. Maybe we want to stop recording before I ask it.